So a heat engine takes advantage of the fact that heat spontaneously goes from a high temperature reservoir to a low temperature reservoir. Heat travels from hot to cold, and you can peel off a little bit of that heat transfer and do work. What about the opposite process? What if you want to transfer heat from cold to hot? That does not spontaneously occur. But we do it, right? Refrigerators exist, air conditioners exist, freezers exist. So everything isn't coming to some central temperature, right? We can, in a refrigerator, take heat energy out of the cold interior of the refrigerator and make it colder, but that heat energy has to go somewhere, right? That heat has to go somewhere. So where does it go? How does it move from a cold reservoir to a hot reservoir if it can't occur spontaneously? Well, the devices that move heat from cold to hot are called heat pumps. A heat pump is any device that moves heat from cold areas to warm areas. Now, to activate a heat pump, you need to put work into the system. Unlike a heat engine, where you can get work out, here we put work into a system, some heat pump, and that work pulls heat from the low temperature reservoir, from the cold reservoir, and dumps it into the hot reservoir. So effectively, for a refrigerator, for example, it takes heat out of the internal area inside the refrigerator, and it dumps it into your kitchen. How does it do that? Well, actually, it doesn't violate the laws of thermodynamics because of the work you put into the system. That work actually goes into compressing the gas. So in the air conditioner in your car or in your home or in your refrigerator, typically what happens is there's a gas in a closed system, like Freon or some other coolant gas, that has a very low boiling point. So effectively what happens in a refrigerator, for example, a motor runs and compresses the coolant into a liquid, and when it does that, the coolant heats up and becomes very warm. That coolant is then pumped through a grating on the back end of your refrigerator. If you've ever looked at the back side of a refrigerator, you can see a lot of metal coils. Those metal coils help the hot fluid that's being pumped through them to transfer the heat spontaneously from the hot fluid to the cooler air in your kitchen. So heat is lost from your refrigerator into the air of your kitchen, warming the air of your kitchen. Then, once that liquid cools a bit, it's aerated. It becomes a gas again. It's expanded. When it expands, it cools dramatically. The temperature drops. That cool gas is then fed through a system inside your refrigerator, and it's colder than the air inside your fridge or the air inside your freezer. So heat transfers from the air inside your refrigerator to this coolant gas, or the air inside the freezer to this coolant gas, warming up the coolant gas, which then goes to the compressor, gets compressed down to a liquid, gets very warm when that happens, which is pumped behind your refrigerator once again. So in both areas, the area behind your refrigerator and the area inside your refrigerator, heat is moving from the hot to the cold. Work is done to compress that gas into a liquid, which heats it up. So that's where the work comes from. Without work into the system, refrigerators wouldn't work. If you don't plug in a refrigerator, it doesn't work. But note, not only is the heat pulled from the cold reservoir and dumped into the hot, the work you do is dumped into the hot reservoir. So you're heating up the hot reservoir, you're putting more heat into the hot reservoir than you are removing from the low temperature reservoir, which is why when you want to cool an apartment or a bedroom, you don't pull in a freezer, plug it in, and open the door. Because what will happen is the freezer or refrigerator will run trying to cool the air inside the now open area for the freezer. That air will get a little bit cooler, but then the air behind the refrigerator or freezer will get much, much warmer. And so plugging in a refrigerator, opening the doors, you will not cool your room, you'll actually warm your room. That's why if you have a wall unit air conditioner or central air in your house, the air conditioner for central air is outside. It's heating the outside air. It's not heating the air in your house. It's actually cooling the air in your house. If you have a window unit, a window air conditioner, one side of the air conditioner is blowing cold air in, but then the hot air is being blown outside, right? It's being pushed. The hot air is being, for the air conditioner, the hot coolant is interacting with the air outside. We don't care if we heat up the air outside, we just want to cool the inside. So that's a heat pump. So heat pumps don't have efficiencies per se, like engines. They have what's called a coefficient of performance. And the coefficient of performance depends if you're talking about a heat pump or a refrigerator. Now, a refrigerator is technically a type of heat pump, but manufacturers for refrigerators, when you look at a coefficient of performance for a refrigerator, it has Q sub L over W. It basically says how much heat can you pull out of the inside of the refrigerator for every joule of work you're doing, right? If for every 1 joule of work that your refrigerator does, right, that much energy, 1 joule of energy, electrical energy used, 10 joules of heat energy are removed from the interior of a refrigerator, then the coefficient of performance would be 10. The coefficient of performance is 25. That means you get 25 joules of heat removed for every 1 joule of energy or work done by the refrigerator. So the higher the coefficient of performance, the more efficient, if you will, your refrigerator. Now for heat pumps, the coefficient of performance is often given as QH over work, not Q sub L. So how much heat do you dump into the high temperature reservoir as a function of work? But you can see that this is kind of related, right? QH is work plus Q sub C. So doing the substitution, coefficient of performances are close to being the same equation, but not quite. The best coefficient of performance you can hope for is, again, a Carnot engine, a Carnot heat pump, if you will. It's the most possible efficient heat pump you can have. The coefficient of performance for a Carnot heat pump is the temperature of the low temperature reservoir minus the temperature difference between the high temperature reservoir and the low temperature reservoir, the cold. So the bigger the temperature difference between hot and cold, the bigger the denominator, the smaller the coefficient of performance. So an air conditioner, if you've ever used the air conditioner on a really, really, really hot day, isn't as efficient as an air conditioner used on a mild day. On a mild day, the high temperature reservoir, which in this case is the outside air, and the low temperature reservoir, which you're trying to drop, the cold reservoir, which is the inside air, if the closer those are to the same temperature, the more efficient your Carnot engine is. But again, we're dealing with temperatures here, not change in temperature, so you must use Kelvin for both the heat engine and the heat pump. Temperatures must be in Kelvin, not Celsius, not Fahrenheit. So this is the effect of a simple heat pump.